In the last lecture, we discussed about bipolar junction transistor, and in this chapter, we will discuss about field effect transistors. Field effect transistors are called unipolar because only majority carriers take part in conduction. Next, these are less noisy device as compared to BJT due to the absence of minority charge carriers. Like BJT, FETs also have a common application, that is, it can be used as an amplifier. A major difference between BJT and FET is their input impedance Ri. Input impedance Ri for FET is very high. We will discuss about this input impedance for field effect transistors. And one more advantage FET have over BJT, that thermal stability. Thermal stability of FET is better than BJT. BJT is in BJT there is large risk of damage due to heat, but in FETs this is not possible. Now we will see classification of field effect transistors FETs. FETs are divided into two categories. One is junction field effect transistor, junction FET, or sometimes called JFET. And second type is metal oxide semiconductor field effect transistors. Metal oxide semiconductor field effect transistor, also called MOSFET or sometimes called IGFET, means insulated gate field effect transistor. In JFET there are three terminals: source, drain and gate, while in MOSFETs there are four terminals: source, drain, gate and one more additional terminal, that is body. Junction field effect transistor have their input impedance in the range 10 raised to power 6 to 10 raised to power 8 ohms, while MOSFETs have their input impedance in the range 10 raised to power 10 to 10 raised to power 15 ohms. Junction field effect transistors are divided into two types, that is N-channel JFET and P-channel JFET. While MOSFETs are divided into two types, one depletion MOSFET and the other is enhancement MOSFET. The depletion type MOSFET and enhancement type MOSFET has a basic difference between them is the channel through which charge carriers will flow. This channel is diffused during fabrication in depletion type MOSFET. Means from the beginning itself, channel will be there in depletion type MOSFET, while in enhancement type MOSFET, channel will be induced during operation. If proper biasing is given to the enhancement type MOSFET, then only channel will induce and device will conduct. One more difference between depletion MOSFET and enhancement type MOSFET is that depletion type MOSFET can operate in depletion and enhancement mode both, while enhancement type MOSFET can operate in enhancement mode only. Enhancement mode only, while depletion type MOSFET can operate in both the modes. It is further divided into N channel, P channel. It is further divided into N channel and P channel. Now we will first discuss about junction field effect transistor JFET. In junction field effect transistor, there will be N-type silicon and it may be P-type silicon, can be P-type silicon, and in this N-type silicon, we will diffuse two P-type materials, and these two P-type materials will be connected together and will form gate terminal for the MOSFET for the JFET. This terminal will be used as a source for this JFET, and this terminal will be used as a drain for this JFET. The length of this region between these two gates is called length L of the channel. This particular region will be called as channel. From this region, N-type region, majority charge carriers electrons will be flowing, and this region is called channel. And this is called width of channel. So now I will define some definitions, some terminologies. First, source. Source is the terminal which will supply majority charge carriers to the channel category, flowing from source to drain. So source is the terminal which supplies majority charge carriers majority carriers to the channel. Number 2, drain. Drain is the terminal which will collect the majority charge carriers from the channel. Now, drain is the terminal through which majority carriers will be leaving the channel. So, from this drain terminal, the majority charge carriers will leave the channel. The third terminal is gate terminal. Gate is the terminal which controls flow of majority carriers from source to drain. So this gate terminal will be controlling the charge carrier flow from source to drain. Now we will see the operation of JFET. Suppose this is N-type semiconductor and these are two P-type semiconductors which are highly doped as compared to N-type region, and by shorting these two P plus semiconductors we get terminal of this JFET. Now we will bias this JFET. Gate will be biased at lower potential with respect to source terminal, so that it is ensured that gate to source is reverse biased. So this battery VGG ensures that gate to source is reverse biased. This voltage, gate to source voltage VGS, will be always negative for this JFET. And drain terminal is biased at higher potential with respect to source terminal. This battery VDD will be responsible for the current flow in the device. According to the terminal of battery, there will be a field in the channel in this direction, electric field. This field is basically responsible for the flow of charge carriers in the channel. Now the voltage between drain and source terminal will be defined as VDS, drain to source voltage, and if majority charge carriers are supplied by the source, means electrons are supplied by the source, these electrons will be leaving the channel from the drain terminal, means electrons will flow in this direction and the drain current ID will be in opposite direction ID. While gate terminal will be through this IG. As this battery is ensuring gate to source is reverse bias, so in reverse bias PN junction the current is very less and we will Now consider this gate current Ig equal to 0 volt. Now this voltage of VGG, for example, it is at some voltage -2 volt, because with respect to source it is negative, and source is grounded means it is at a zero potential, and with respect to source drain is biased at higher potential means it is somewhat at +5 volt. If we see P-type material is at negative potential, N-type material is at positive potential, means this is a reverse biased junction. Between drain and gate there is reverse biasing. And also if we see P-type material is at -2 volt and N-type material is at zero potential. So there is reverse biasing between gate and source also. But there is difference in the reverse biasing. If we see the difference here, the voltage difference is around 7 volt and the voltage difference here is 2 volt. So now I can say that the reverse biasing between gate and drain is more than reverse biasing of gate to source. So the depletion layer now we will draw. As P type region, gate region is highly doped, the depletion layer in this region will be very less. Depletion region in this region very less, and I am not showing it. N-type region is lightly doped as compared to P plus region, so the depletion layer will penetrate in this region. And the depletion layer will be like this. Exactly, this will be the shape of depletion layer in J. Here the depletion layer width is more because the reverse biasing of gate to drain is more than gate to source. So the depletion layer will penetrate more there. The width of the channel will be less near drain. So we can say that depletion layer width is more towards drain end, and width of channel, that is region between two depletion layers, width of channel is less towards drain end. And the shape of channel is wedge shape. The channel is has width more towards source end, and as we go towards drain end, the width of channel decreases. Now we will draw the characteristics for JFET. First we will draw transfer characteristics. Transfer characteristics will be drawn between ID and gate to source voltage VGS. Sorry. Negative gate to source voltage is applied, and we will see the drain current ID. In JFET, Now, if voltage VDS is applied to the JFET, the field will be set up in the channel, and due to this field, charge carriers will start flowing and drain current ID will flow to the device. If VGS equal to 0 volt, this voltage between gate to source voltage. If VGS equal to 0 volt, the depletion layer width will be somewhat like this. It will be more towards drain end and less towards source end. But if we increase VGS in negative direction, means this voltage is made more negative, minus 3 volt, minus 4 volt, then the reverse biasing between this P plus and this N channel will be increasing, and between this P plus and this N channel will be increasing, and with increasing reverse biasing, the depletion layer will penetrate more into the channel. So when VGS equal to 0 volt, the width of the channel will be maximum and the drain current ID will be maximum, that is ID access. Now if we go on increasing this VGS, gate to source voltage VGS, if we go on increasing this VGS, reverse biasing between gate and drain, reverse biasing between gate and source increases, and with increase in reverse biasing, the depletion layer penetrates more into the channel. If the channel width decreases, the current through device decreases, and for a particular value of VGS, the depletion layer on both the sides will touch each other and the channel will be cut off. Channel will be cut off, and in this case, the drain current ID will be equal to 0. This voltage is called VGS cutoff or VP, pinch off voltage. Called pinch off voltage. These are the transfer characteristics of N channel JFET. There will be similar characteristics for P channel JFET. For P channel JFET, the characteristics will be like this. We will apply positive VGS in order to make gate to source junction reverse bias. Now we will draw transfer characteristics, drain characteristics for JFET. Number 2. Drain characteristics are plotted against drain current and drain to source voltage by keeping VGS equal to constant. Earlier we kept VDS equal to constant, and this time we will keep VGS equal to constant. Now This time we will keep this VGS at a constant value and we will vary this voltage VDS. If this voltage VDS is varied, the field in the channel will vary. Along with this field, there will be variation in the reverse biasing between drain and source. Only drain and source. If drain and gate. If gate is kept at -2 volt and initially drain to source voltage and initially drain to source voltage is for example +3 volt, then the reverse biasing will be 5 volt. If we increase it to 5 volt, then the reverse biasing will be 7 volts. Means with increasing drain to source voltage, the reverse biasing between drain and gate will be increasing. When VDS equal to 0 volt, VDS equal to 0 volt, the field in the channel will be equal to 0. If the field is 0, then there will be no flow of charge carrier and then current ID will be equal to 0. Now, if we increase VDS is increased, then reverse biasing between drain and gate will be increasing. Also, the field in the channel will be increasing. So now the depletion layer width can be seen like this. But with increase in electric field, the charge carrier flow will also increase, and at lower voltages of VDS, it is seen that drain current ID increases linearly with applied VDS. Further increase in VDS will further increase the reverse biasing and hence depletion layer width. But with increase in depletion layer width, the field is becoming stronger. This field EV is becoming stronger, and charge carriers will flow with higher velocities and will determine higher drain current, and the current will continues to increase linearly with VDS. At a particular value of VDS, both the depletion layers will touch each other, and in the earlier case, at this point, the drain current ID was reduced to 0. But this time, at this voltage, this field, electric field E, is sufficiently strong to maintain the flow of charge carriers electron through this gap. Means this electric field will not allow both the depletion layers to touch each other. There will be always a small gap between these two depletion layer, and through this gap, this depletion layer will maintain flow of charge carrier and drain current ID will continue to flow. But at this voltage of VDS, the velocity of charge carriers will saturate and they will move with constant velocity and hence will carry a constant current. So at this point, this voltage is called pinch off voltage Vp. At this point, drain current ID saturates. At this point, both the depletion layer touches each other, and at this point, this voltage is called Vp. Remember that this voltage Vp is different from the voltage that was seen earlier. Now, if we change the value of VDS, means we will set VGS at any different voltage and it will be kept constant. So, if we set VGS equal to 0 volt, then we will obtain this graph. If we set VGS equal to -2 volt, then we will get same graph, but it will be drawn below, and these will be the curves for higher values of VGS. This curve will be for VGS equal to 0 volt and this curve will be equal to 0 volt for minus 2 volt and this curve will be for VGS equal to minus 4 volt. These are the drain characteristics of JFET. Now we will see some basic definitions about related to JFET. First, drain current ID. Drain current ID. Drain current ID is mathematically given by ID equal to ID SS into 1 minus VGS upon VGS cutoff. This VGS cutoff is sometimes written as pinch of voltage VP. So drain current ID can be written as ID equal to IDSS into 1 minus VGS upon VP. Sorry, it's square. Now drain current ID depends on square of VGS. If it depends on square of VGS, JFET is called as square law device. It's called square law device. Next term related to JFET will be its transconductance. For JFET, its transconductance GM is defined as GM equal to del ID upon del VGS at constant VDS. We know the equation for drain current ID. It is IDSS to 1 minus VGS upon VT whole square. Differentiating this with respect to VGS, we get GM equal to IDSS into 1 minus VGS upon VT into 1 upon VT minus 1 upon VT. So rewriting it as minus 2. So it will be 2 into 1 minus VGS upon VT and IDSS will be equal to minus 2. Transconductance GM will be equal to minus 2 IDSS into 1 VT into 1 minus VGS upon VT. This will be the equation for transconductance of GM. Now, in this equation, if VGS is made 0, then the transconductance will be maximum. That is, at VGS equal to 0 volt, GM will be maximum, and maximum GM is given by GMO equal to minus 2 IDSS upon. So now I can write transconductance GM equal to GMO into 1 minus VGS upon VT. Well, this term is maximum transconductance. Now the next term will be drain resistance. This drain resistance is defined as RD equal to del VDS upon del ID at constant VGS. And last term is amplification factor. Amplification factor. The amplification factor is defined as mu equal to del VDS upon del VGS at constant ID. And also it is written as mu equal to Gm into RD. So transconductance and then resistance RD, the product will be amplification factor for JFET. Now we will solve some problems on JFET. And N channel JFET has IDSS equal to 2 milliamperes and Vp equal to minus 4 volt. Calculate its transconductance Gm when VGS equal to minus 2 volt. This question was asked in GATE 1999 in electronics paper. We know that transconductance of JFET Gm is equal to minus 2 IDSS upon Vp into 1 minus VGS upon Vp. Putting all the values, we can get the transconductance of JFET as minus 2 into 2 milliamperes divided by minus 4 volt into 1 minus 2 by minus 4 volt. Solving this, we get minus 4 into 10 raised to power minus 4 divided by minus 4 into 1 by 2. It will be 0.5 millisiemens. Next question. Calculate the drain current ID for JFET with AP equal to minus 4 volt and VGS equal to minus 2 volt with IDSS. This JFET has IDSS equal to 10 milliamperes. Now ID, drain current ID equal to IDSS into 1 minus VGS upon VT. This simple equation equals to what? This equation can be used to calculate ID. IDSS is given 10 milliamperes and 1 minus VGS is given minus 2 volt divided by minus 4 volt whole square. This will be equal to 2.5 milliamperes. This will be drain current ID at VGS equal to minus 2 volts. Next, calculate transconductance Gm when ID changes from 3.1 milliamperes, sorry, from 1.3 milliamperes to 1 milliamperes with change in VGS from minus 3 volts to minus 3.1 volts. Transconductance Gm. We know that transconductance Gm equal to del ID upon del VGS at constant VDS. Using this equation, I can write this change in ID equal to ID2 minus ID1 and this change in VGS as VGS2 minus VGS1. ID2 is 1 milliamperes and ID1 is 1.3 milliamperes, while VGS2 is minus 3.1 volt and VGS1 is minus 3 volt. So minus of minus 3 volt. It will be minus 0.3 into 10 raised to power minus 3 divided by minus 0.1 volt. This will be in ampere. It will come out to be 3 millisiemens. This will be the transconductance Gm for this J. So this was all about JFET. Now we will move to MOSFETs, metal oxide semiconductors. But before moving to the MOSFETs, we will discuss something about MOS capacitor. MOSFET's operation is somewhere depends on this MOS capacitor. MOS capacitor has a simple structure. It has a P-type or N-type semiconductor on which an insulating layer is developed, which is silicon dioxide SiO2 insulating layer. And above this metal plate will be there, and nowadays in modern MOSFETs this metal plate is not used. Instead of this metal, P plus polycrystalline silicon is used. Silicon is used. If it is N-type substrate, then it will be N plus polycrystalline silicon. So in this structure, this upper part is metal, middle part is SiO2 insulating layer, and the lower part is a semiconductor. So this structure is called metal oxide semiconductor MOS. And this terminal is, we will call this as gate terminal, and this terminal will be grounded. This will be called as body terminal for this MOS capacitor. Now we will see the operating modes of this MOS capacitor, which will be later on used in MOSFETs. Depending on the voltage at the gate terminal, that is voltage VG, a MOS capacitor operates in 3 different modes. Number 1 is accumulation mode. We have a MOS capacitor with p-type substrate, and this substrate is kept at ground terminal, ground potential, while we will apply a negative potential at this metal terminal, gate terminal. If we apply a negative potential to the gate terminal, then the gate metal will be negatively charged, and this negatively charged gate metal will attract the positive charges that are holes near this oxide semiconductor interface. This is nothing but accumulation of holes when negative potential is applied. So a MOS capacitor will operate in accumulation mode when a negative gate potential is applied, that is Vg is negative. Now in accumulation mode, we can see that this particular region is conducting region, this particular region is conducting region, while in between these two conducting region there is non-conducting region, so it can be seen as a parallel plate capacitor. If this is the thickness of oxide layer, then in accumulation mode the capacitance of this MOS capacitor will be oxide capacitance, and it will be written as epsilon A by P oxide, where epsilon is equal to epsilon naught into epsilon r, epsilon naught equal to 8.854 into 10 raised to power minus 12 farad per meter, or it will be equal to 8.85 into 10 raised to power minus 14 farad per centimeters, while epsilon r is the relative permittivity of SiO2. Permittivity of SiO2, and it is equal to 3.9. Now the capacitance can also be written as C oxide equal to epsilon upon P oxide. Here we have not considered this area, so the oxide capacitance can be written as farad per meter square in this case, and here the unit of capacitance will be farad. So in accumulation mode, when a negative potential is applied to the gate terminal, the positively charged carriers of p-type substrate will be accumulated near oxide semiconductor interface, and this mode of operation is called accumulation mode. If we have n-type substrate instead of p-type substrate, then to operate it in accumulation mode, we must apply a positive voltage at the gate terminal. So this positive gate metal will attract negatively charged electrons in this region. In this case, the accumulation will be due to electrons. Now the second mode of operation is depletion mode. Now this time we will apply a positive voltage. Vg will be positive, but this voltage will be less than voltage which will be defined later called threshold voltage. If the applied gate voltage is less than threshold voltage, then the gate metal will be positive. But this positive voltage is not sufficiently strong to, this is P type substrate. This positive gate metal is positive voltage to the gate metal is not sufficiently strong to attract the negatively charged carriers, which are very less in this P type substrate. So this voltage is sufficient only to repel the holes away from the oxide semiconductor interface. If these holes are repelled away, then such a region will form here where there will be no charge carrier. There will be only ions. So a depletion layer will form. Depletion layer will form, and this mode of operation is called depletion mode. This is the oxide layer, and this is bit of depletion layer, that is extreme. Now we can see this is the conducting region and this is the conducting region. Now all the charge carriers in this particular region are repelled away, and because there are no charge carriers in this region, we can say that this region is also a non-conducting region along with this. So there will be two capacitances, one capacitance in oxide layer, other capacitance due to this depletion layer. There will be two capacitances in series. One capacitance will be oxide capacitance, other capacitance will be depletion capacitance, which will be called CD. The oxide capacitance we already have seen equal to epsilon upon T oxide, and it will be written as epsilon naught into epsilon R of SiO2 divided by T oxide farad per meter square. The depletion capacitance will be written as epsilon upon XD, width of depletion layer, and epsilon will be epsilon naught into epsilon R, but is in case of silicon, because this is not silicon oxide, it is silicon material, which is a type of, which is a part of this P type substrate. So divide by XD, this will be the capacitance, and due to depletion layer in farad per meter square. The total capacitance in depletion mode will be C equal to 1 upon the total capacitance C is the series combination of both the capacitances, will be written as 1 by C equal to 1 upon C oxide plus 1 upon CD. So total capacitance C will be equal to 1 upon C oxide plus 1 upon CD. It can also be written as C oxide into CD upon C oxide plus C. This will be the total capacitance in depletion mode. Now the third mode of operation is called inversion mode. This is more important than the other two modes of operation. Inversion mode. This time again we will apply a positive voltage to the gate terminal, but this time this voltage will be greater than this threshold voltage. Threshold voltage, if the applied voltage is greater than threshold voltage, then this voltage, applied gate voltage, will be sufficient to attract the negatively charged carriers which are very less in this p-type substrate. So these electrons will be attracted towards oxide semiconductor interface, and now there is no depletion layer in this particular operating mode. So this time there will be only oxide layer, non-conducting layer. So the capacitance will be equal to C oxide equal to epsilon Si epsilon naught into epsilon R of SiO2 divided by P oxide. This will be the total capacitance of most capacitor in inversion mode. This is the inversion layer of electrons. If it is n-type substrate, then inversion layer will be due to holes. Now we will draw the capacitance curve for MOS capacitor. If we apply a negative gate voltage, then will operate in depletion mode, and in the depletion mode the capacitance is C oxide. When we apply positive gate voltage but less than threshold voltage Vt, the capacitance will be the series combination of two capacitances, and it goes on decreasing as the voltage increases. When the voltage Vt is crossed, the capacitance again becomes oxide capacitance, C oxide. This is the capacitance curve. The maximum capacitance is C oxide, and this is the minimum capacitance. This minimum capacitance will be C equal to 1 upon C oxide plus 1 upon CD minimum, and CD minimum will be equal to epsilon naught into epsilon silicon divided by XD maximum. So we can get this C minimum capacitance. This region will belong to depletion mode, and this region will belong to inversion. Now in most capacitors, if the frequency of gate voltage Vg is very high, then in that case inversion layer could not form. Inversion layer could not form. If inversion layer cannot form, then the capacitance in inversion mode also remain at its minimum value.